So here's one of those VS2812 LED strips running. It's actually not exactly that one, because this one also has a white LED, so it has 8 extra bits that I have to send in the bit stream. Let me show the example that makes this happen. So right now it is under examples, and at the bottom we have this VS2812 native example here. And then we have the driver, which is, well, just a bunch of bytes that you can load into memory with the load native lib function as usual. And when you load this to memory, then it will give you a few extra extensions. So first one is to initialize it, and then one to set the color, and one to set an overall brightness that you always will scale the colors with. And I wrote it so that it uses DMA, direct memory access, and also one of the timers. So in this case you can choose timer 3 or 4, and you can use channel 1 or 2 on either of them, so you have 4 different pins to choose from. And I wrote them down here. You can probably implement this for more than one driver timer, but these are the common ones on the VESC-based hardware that is out there that I'm aware of. And timer 3 is channel 1 and 2 in timer 3 is Hall sensor 1 and 2 on the VESC-6. And timer 4 channel 1 is the PPM port. Now the PPM port will not work, because you have to, there is a low pass filter on the input, so there's a lot of capacitance for the CPU to drive that output, and it can't really do that at the high bit rate that is required for this one. So in this case I have it connected to Hall 1. So when you use this one you have to, well, it's not the best interface, but it's kind of a quick demonstration driver that I wrote. So instead of having symbols, you have to pass 0, 1, for example. If you do 0, then you have channel 1. If you pass 0 to use timer 4, then you use timer 3. And then you have one flag for this RGBW, which means that if you have the white one, then it will send 32 bits instead of 24 per LED, and then you can address the white one as well. And that is the case for this one. So you set this up, and when you set it up, it will also allocate memory on the LBM memory that it will use for the bit buffer. And it's not very memory efficient, because every single bit needs 16 bits or 2 bytes in memory, because that will be translated into a duty cycle that the timer will send out with DMA. So you can use something like 100 LEDs at most before you start to run out of the LBM memory. So at this point we have it initialized, and then I made a table with colors, and then I made a regular while loop that just goes on forever, and then we loop over all the colors, and for every color we loop over all the LEDs, and then from every LED we switch off the previous one and switch on the next one. And this one has an if statement here, because if we are at LED 0, then the previous one would be less than 0, and that means we have wrapped around, so it means that we should switch off the last one instead. And then we sleep for 50 milliseconds, so we update them at 20 Hertz now. And you can see that since this is done with DMA and we only have to use the extensions provided by the driver, we use almost no CPU at all. We are way below 1% on average here. So that is working really well. I can also show another thing. This will be a live demo, because I have actually not tried this before, but it should work to have more than one library loaded at the same time if you write them in the way correctly, so that they don't overlap in memory regions and so on. So let us try the cube native library, where we draw this 3D cube on this display. And then I will let's run this one by itself to start with to see what it looks like. Then this one will stop. And then we draw this rotating cube here that has high frame rate now, because we have this accelerated line drawing algorithm here. So I will take the code from here and up and just paste it to the end of that file. Before this loop actually. And then I will modify this one a bit, so you know, when you enter a loop like this, then it will not leave. So if I would put it here, then it would only run this one loop as it never leaves it. So instead of making it a loop, I will make it a function. And we call this function LED. Doesn't take any arguments. And at the end of the function, let's see, we'll make this a progn. Let's indent everything another step. See a lot of parentheses here now, and then we should be down here, I think, and then we'll just call the LED function again. So now we make a loop by making a recursive function instead, and then we can spawn a thread that runs this function, and after the spawn it should continue down here. Spawn, and let's give it 100 bytes of stack, and then call the LED function. Let's see if this works. Okay, so the cube is rotating, but the LEDs are not updating. See if we got any print in the console. Out of stack. Yeah, maybe we need to give it a bit more. Let's give it 150 bytes instead. Out of memory. Yeah, that is something that can happen too. Yeah, so much for this live demo. Maybe if I comment this one out, just want to see why it runs out of memory here. Yeah, we do have a lot of arrays in the code now, so that might be the issue. We can only initialize 5 LEDs, so then it should require a bit less memory for the LED driver at least. And if it doesn't spawn this one, what happens then? Yeah, then we do get the rotating cube. Maybe I did something crazy here to make this one not tail recursive or something like that. So just do it run. You can try to run it one iteration, see, without doing this thing at the end. Maybe I even discovered a bug here live now. Yeah, we did it one time and then it stopped, so I think there is something strange going on there. Another way to do it would be to do it like this as well. Maybe that's easier to read even if we make this a while loop internal instead of a recursive function with a progn. Alright, that seems to work. Maybe we can go for 10 LEDs now again. Yeah, so now we have all of the LEDs running, and we have a smooth rotating cube that updates at, let's see how much that is if we zoom in a bit. Yeah, at 23 frames per second or so, using 2 native libraries at the same time. So that is quite nice, and I will investigate this later. Hopefully it's easy to solve. So let's look at the additions that I made to the native library loader to make things like this possible. So here is the Git repository, and then we are in LispBM and clibs. And a reminder that everything that is in here that is not linked to the rest of the VESC code at the moment. So you could build a library with just these files, and it is not a lot of files. In fact, the thing that takes the most memory here right now is the STM32 standard peripheral library. And you don't even need it. For example, the cube doesn't use it at all. I use it for the LEDs because that was a nice challenge to get the DMA and everything running in a native library and figure out how to deal with that. So let's look at the LED example. So if you look at the make file right now, so in order to use the SD library, you have to set this thing to true. And you can even set it to true even if you don't use it, because if you don't use any function, then the linker will remove all of the unused functions, so it will probably not even grow in size. And when it comes to size, you can see that the reason that this takes so much space is mostly because the SD library is quite bloated when it comes to initializing all the things and so. So you could make this probably in a third of the size. But the LED driver, or the driver that does the line drawing on the LCD, you see that is much less code when it loads the extensions and everything. But even so, this is loaded into RAM now, and later when I have added support for loading this into Flash, it will not take that much at all of the total memory. You can actually check how much it takes. So if you do bufflen WS2812, then we can see that this one is 2.8 kilobytes long, and this flash page has 128K, so you can run, this takes a bit more than 2% of the total flash memory if you would run it on Flash, which we're not doing now, we're running it in RAM. So when that is working, which should be fairly easy to implement, then you can load lots of libraries at the same time. We can also look at this one, I think this was the name. Yeah, this one is less than 400 bytes, so that is nothing, even if you load it in RAM. So anyway, going back here, you see that you have to use this one, and then the same thing as before. Now the C library path is 2 levels down, because I moved these things into an example folder, and before they were directly in the clibs folder. So let's open the code. So what changed from before is that now at the beginning of the code you have to add this header define. This might change a bit as well, but this one I had to add in order to get access to this argument pointer from everywhere in this file, and have that on the relative memory location where this library is loaded. I will not go into the details about that, but that was one of the implications on how I write the code to make that work. And then at the end you have I put it in the end, you have the init function where you register your extensions and set this argument to 0 that you can reuse later. And then when I initialize the library, that is a Lisp extension where you initialize it. And at that point you will actually use the memory allocation functions of LispBM to allocate the amount of memory you need for the amount of LEDs that you have initialized for, and it will actually check if the allocation was successful. So if you try to allocate too many LEDs, like more than 120 so, and you run out of memory, then it will return evaluation error, and it will also give the reason not enough memory. So it does that checking there. And then when you have set up this structure, then it will, and it was successful, then we call this init function, which is internal, that does all of this regular using the SD library stuff to set things up with DMA. And then the other functions will essentially, so after you did this, then nothing will be running, then just the direct memory access with the timer will output all the bits, and then the set brightness and the set color functions only update the bit buffer, and then the DMA will update the new value on the next time you run it. So that is really nice that you could get all of that running as a library like this, that is also independent of the position, so you can load it on any hardware without compiling it into the firmware itself. So that is this one. Now I also had another example where you can use where I'm using a thread. This one is a lot shorter, and this one doesn't need the SD library at all. And this is probably, if you're going to do something like the balance app that run in their own applications, then you're going to do something like this. So in this case, in the init function, I also show how to store some data. You don't need that to run a thread, but this is one way to do that. So we have this data structure, and when we run the init function, we allocate memory for it, and then we just set some numbers in A and B, and then D, we give it a pointer to the thread that we just create. So we have this spawn function now in the VESC interface where we can create a spawn a thread. And this one, you don't have to take care of the allocation yourself for it. You just give it a function and you tell it how much stack you want. You usually don't need that much stack, but in this case we have a printf in here, and then you need to give it, then this one will require quite a bit of stack, so that's why we need to have 1 kilobyte of stack here. And then you give it the name of the thread, and in the end you give it an argument, and this argument in this case is the pointer to this data structure that they allocated. And then when you're done, you also set up a stop function that will stop the thread when you're done with this one. And then I'll just print something and return, and then it will spawn this thread. And the thread will just, well, it will cast the argument back to this data structure, so you have access to it here. And then it will run as long as you don't tell it to terminate. And then it will just print hello THD and increase the B number in it, and then it will sleep for a second. Let's try this one actually. I don't think I have put it in VESC tool, but we can just open a new tab here. Let's open a terminal in here and do make. Then we get this example.lisp, and you can see this one is also really short, so even the thread that does all the printing and everything doesn't take many bytes at all. So that is how efficient it is to compile libraries like this. So now we put it here and upload the code. And that did not do much. Did we even disconnect? No, we're still connected. See if we can upload the other one again if it still runs. Yeah, it does. Let me pause for a bit and see if I can figure out what went wrong. Okay, there I pressed resume again, and I just realized that I never loaded the library, I just pasted it in here. So let's load the library and see. Hopefully that works on the first try. Load and upload. Yeah, and you see that we got hello thread and hello example. And the reason that we got hello thread first, if you look at the code here, then we can see that we spawn the thread first and then we run this code here. And I think this thread will get normal priority, while this one has, this is the LispBM value, which has a bit less than normal. And then this one will run first. So that is working. And if we do reset, then you see that it has counted to 33 and it will print terminated, and then we'll start it again. And that is when because when we do reset, then we call the stop function. And the stop function will print the result, and it will request for the thread to terminate. And what this function does, it sends the signal to this thread, and then it waits for this thread to exit. So if this thread doesn't check this thing, then it will get stuck here forever. And then when it's done, it will print terminated, and then it will deallocate the memory of the data and return. And yeah, so that we should also see if you go and load this example. So every time we upload code, it will go over all the libraries and call the stop function if they are registered. So we got this again. We got the result terminated, and now we run the other code. And hopefully that is still working. And that seems to be the case. So yeah, not that much work to get the thread running either. Next up is to add a lot of the MC interface functions to deal with that. Deal with motor control as well if you want to do it from within a C library. So yeah, I think this is really cool and really promising. You can have as many libraries as the memory can fit, and they can run at the same time, and they can even run threads. And yeah, by the way, I forgot to show this about the threads. So when you run the thread, you see that we registered this one under libthread. So if you go to the VESC terminal and type threads, then it should show up here. Yeah, and you can also see how much stack you have left. And then if you go to this example again, and type threads again, then you see that this one is gone here now. So it stopped it nicely. And also when you start threads and allocate memory here, so even when you allocate this thread will allocate it on the LBM memory. So if you give it more memory, we can try that actually as well, now that we're at it. So run this one again. So now you see that we have 22% of the LBM memory used. And if I go to the code and I give it 2048 instead, save, compile, and copy paste this. Maybe we'll add something to VESC tool to automate these steps at some point, but this is still at the proof of concept stage. And now we upload it again. Yeah, so we went from 22 to 29, and the other part of the memory is mostly for the Lisp extensions. So even when you run threads, so you get a really good overview here of how much memory you're using for the development that you do. Same thing with the malloc and free that you use from here. Another small thing to point out is see that I do VESC interface.free here when I stop it. But even if you wouldn't do that and restart LispBM, it will free all the memory that is allocated by libraries. So it will not get the memory leak by using the alloc function of the malloc function of the C library in the VESC. So that is also an advantage. So really cool and really convenient to, well, the development like this. That's what I had for now.